We begin with a definition. Let T be an operator on a vector space V. So T acts on from V to itself. A subspace U in V is invariant under T if for every vector U in the space U, T of U belongs to the subspace U. So here the requirement is that when we act by operator T on vectors from this subspace, then the values that this operator will produce will still belong to this subspace. Sometimes we use the following notation. So we will write that T applied to the subspace U sits inside U. So this is another way to express the fact that U is an invariant subspace for the operator T. The idea here is that when we try to understand the structure of operator T, then invariant subspaces may help, because now what we can do is we can view T not as an operator from V to V, but as an operator from U to U. Thus, we can construct an operator now on a smaller space. And by reducing the problem to a smaller problem, we can better understand the structure of operator T. Let us give some examples. So what are one-dimensional invariant subspaces? Suppose a one-dimensional space U, which is spanned by a single vector V, is invariant under T. So what does it mean? So this means that when we apply T to a vector V, the result is still in the subspace U, and thus we get that T of V is a multiple of a vector V. But this means that V is an eigenvector for T with eigenvalue A. So we see that one-dimensional invariant subspaces correspond to eigenvectors of operator T. We always have trivial invariant subspaces. So these are zero space and V itself. So this smallest possible space and the largest possible subspace, they are clearly invariant under the action of any operator on the space V. For our next example, let us consider operator of differentiation on the space of polynomials. So here, if we take as Pm the subspace of polynomials of degree less or equal to n, then we see that this subspace is invariant under this operator of differentiation. So indeed, if we differentiate a polynomial of degree n, then we obtain a polynomial of degree n minus 1. And so the result will belong to the same subspace. Let us also consider subspaces P even and P odd. So these are subspaces of even or respectively odd polynomials. So recall that a polynomial is even if f of minus x is equal to f of x, and the polynomial is odd if f of minus x is equal to minus f of x. So these spaces are not invariant under the operator of differentiation. So one can check that the derivative of an even polynomial is odd and the derivative of an odd polynomial is even. But the spaces are invariant under the operator of the second derivative. So if we take an odd polynomial and differentiate it twice, then the result will be an odd polynomial. For our next example, so let us consider V lambda. So this is the lambda eigenspace of operator T. So then we claim that V lambda is invariant under T. So indeed, so suppose vector u belongs to V lambda. So what is T of u? So T of u is equal to lambda times u. But if we take a vector in a subspace, then any multiple belongs to the same subspace. So this belongs to V lambda. And by definition, so this tells us that V lambda is an invariant subspace. Now let us try to understand what is the relationship between invariant subspaces and the matrix of T. Let U be an invariant subspace for T. Choose a basis in U, say U1 through UK, and extend it to a basis of V. Now we get a basis B that starts with basis vectors of U and then has some extra vectors, Vk plus 1 up to Vn. Now, what can we say about the matrix of operator T in basis B? Our rule for constructing a matrix of a linear operator is that we need to find images of basis vectors and then expand these images again in the basis. So we start with T of U1. So here U1 is a vector in the subspace U, and this subspace is invariant. So this means that T of U1 is a vector in U again. And hence, so T of U1 belongs to the span of the first k basis vectors. And so we can expand T of U1 as A11 U1 plus A1k UK. And we don't need the remaining vectors in this expansion. So here we're going to put 0 times Vk plus 1 plus 0 times Vn. And the same will be true for the first k basis vectors in B. So T of UK, for example, will be AK1 U1 plus AKK UK plus 0 times Vk plus 1 plus 0 times Vn. The remaining vectors do not belong to the invariant subspace. So if we take t vk plus 1, so then in the expansion we will get all basis vectors. So we'll get ak plus 1, 1, u1 plus ak plus 1, k uk plus ak plus 1, k plus 1, vk plus 1 plus ak plus 1, n vn. Now, what can we say about the matrix of operator t in this basis? So what we do is, once we have computed images of basis vectors, so we place their coordinates as columns to form a matrix. So this will be transformed into the first column of the matrix. And what we see is that this matrix will have the following structure. So if we look at the first k rows and k columns, then what we will see is that, well, we'll have some coefficients here, but all coefficients in this corner will become 0, right? So these are these 0 tails of these expressions. And for the last n minus k columns, we have no restriction on the coefficients, so they can be completely arbitrary. So what we see is that we get a matrix with a corner of zeros. So if we get a matrix with a corner of 0, so this means that we have a k by k square and the zeros underneath, this indicates that the subspace that corresponds to the first k basis vectors is an invariant subspace with respect to this operator. Let us prove the following proposition. Let t and s be two commuting operators on a vector space V. So the fact that they are commuting means that the composition of t with s is equal to the composition of s with t. Then kernel of s is an invariant subspace for operator t. Let's give a proof. So what do we need to prove? So we need to prove that the kernel of S is an invariant subspace for t. What does it mean? So we apply the definition of an invariant subspace. So this means that for every vector u in the kernel of S, we have t of u also in the kernel of S. When we need to prove a statement that starts with a universal quantifier, we say let u be an arbitrary vector in kernel of S. We need to show that t of u belongs to the kernel of S. But what does it mean that a vector belongs to the kernel of S? By definition, the kernel consists of vectors that are annihilated by the operator S. So this happens if and only if S applied to t of u will produce a 0 vector. So let us calculate S of t of u. So this is the composition of S with t applied to vector u. But by the assumption of this proposition, these two operators commute. So the composition of S with t is the same as the composition of t with S. So what we get is that this is t composed with S applied to u, or t of S of u. However, we said that u was a vector in the kernel of S. So this means that S applied to u is 0. So from here we conclude that t of S of u is equal to t of a 0 vector, and this is a 0 vector. And thus the conclusion is that T of U belongs to the kernel of S. And this means that kernel of S is invariant under T. As an illustration, we can say the following, that T commutes with operator I, with identity operator. And also T commutes with itself, because clearly T composed with T is equal to T composed with T. From here, we conclude that T composed with T minus lambda I is equal to T minus lambda I composed with T. And then, by our proposition, if we call this operator S, then we obtain that the kernel of T minus lambda I is invariant under T. But this is something that we have already seen, because the kernel of T minus lambda I is the lambda eigenspace of operator T. So we see that V lambda is invariant under T. Now let us state the following theorem. Let T and S be two commuting operators on complex vector space Cn. Then T and S have a common eigenvector. So this means that there exists a vector V in Cn, which is non-zero, and T of V is equal to lambda V, and S of V is equal to mu V. For lambda and mu, some complex numbers. So this vector V is simultaneously an eigenvector for T, and it's an eigenvector for S. What's important here is that these two operators commute. So the composition of T with S is equal to the composition of S with T. Let's give a proof. Since the field C is algebraically closed, so this means that every polynomial of degree greater or equal to 1 has a root. So in particular, a characteristic polynomial has a root. So this tells us that S has an eigenvalue. Of course, here we assume that n is greater or equal to 1. And let's call this eigenvalue mu in C. Once we have an eigenvalue, we know that the corresponding eigenspace, or the kernel of S minus mu times I, is non-trivial. So this is not just a zero vector. Whenever mu is an eigenvalue, we are guaranteed to have a non-zero eigenvector, which is a vector in this space. We note that T commutes not just with S, but also with the identity operator. And thus, T will commute with S minus mu I. This tells us that by this proposition, that the space U, which is the kernel of S minus mu I, is invariant under T. Now, view T as an operator on this invariant space U. Here, U is a finite dimensional vector space over the field of complex numbers. And we know that any operator on a finite dimensional vector space over a field of complex numbers has an eigenvalue. So from here it follows that T has an eigenvalue, and thus an eigenvector V in the space U. So what we conclude is that T applied to a vector V is equal to lambda times V for some lambda in C. But we have that V belongs to the space U, which is the kernel of S minus mu I. So this tells us that S applied to V is equal to mu times V. And so this tells us that V is a joint eigenvector. So the plan of this proof is to consider a non-trivial eigenspace for the operator S, then show that this subspace is invariant under T, and then restrict T to this non-trivial subspace. And in this subspace, we can find an eigenvector for T, but any vector from this subspace is automatically an eigenvector for S. So this non-zero vector that we construct is simultaneously an eigenvector for T and for S. Next, we would like to describe invariant subspaces for diagonalizable operators. We state the following theorem. Let T be a diagonalizable operator on a finite dimensional vector space V. And we know that for a diagonalizable operator, the vector space decomposes in the direct sum of eigenspaces. So here V lambda j eigenspaces for T. Let U be an invariant subspace for operator T. Set the subspace U lambda j to be the intersection of U with the eigenspaces for T, with V lambda j. So j here from 1 to k. Then the claim is that the space U is a direct sum of the subspaces U lambda 1 plus U lambda k. This theorem says that any invariant subspace for operator T is determined by its intersection with the eigenspaces, well, provided that T is diagonalizable. Conversely, so if we take any subspace inside an eigenspace, this subspace will be clearly invariant under the operator T. And this direct sum of such subspaces will also be invariant under operator T. So this theorem gives a complete description of all possible invariant subspaces for a diagonalizable operator T. Let us prove this theorem. So what do we need to prove? We need to prove that U is this direct sum. So this means the following, that we need to show that for every vector U in this invariant subspace U, two things hold. First, that we can decompose U in the sum U1 plus UK for some vectors Uj in the spaces U lambda j. And secondly, that such a decomposition is unique. So there is only one way to write U as a sum of such vectors. So this is what it means that the space U decomposes in the direct sum of its subspaces. What we know is that we have a decomposition for the space V, and U, being a vector in a subspace, also belongs to V. So what we can write is we can decompose U in the sum U1 plus UK, where Uj belongs to the subspace V lambda j. But we need to prove something stronger. So we need to show that these vectors Uj belong not just to V lambda j, but belong to the V lambda j intersected with U. So which is the subspace U lambda j. What we have is that our vector U belongs to this invariant subspace U. And let us change notations and call this vector also W1. And so W1 is the sum U1 plus UK. And this vector belongs to the subspace U. Now let us apply operator T to both sides. On the left, we get T of W1, and let's call this W2. And on the right, we have a sum of eigenvectors for our operator T. So the result will be lambda 1 U1 plus lambda k UK. Now let us do it again. So let's denote by W3 T of W2. And the result on the right will be lambda 1 squared U1 plus lambda k squared UK. And let's repeat this until we come to the vector WK, which is T of WK minus 1, and which will be lambda 1 to the k minus 1 U1 plus lambda k to the k minus 1 UK. What we have here is that the vectors W1 through WK are expressed as linear combinations of vectors U1 through UK. But the coefficient matrix of these expansions is the Vandermonde matrix. And since all these eigenvalues are distinct, so we know that the determinant of the Vandermonde matrix is non-zero. So this tells us that it is invertible. And then we had a proposition that said that if we have such a linear relation between two groups of vectors with an invertible matrix, so this tells us that we have the opposite, that the vectors U1 through UK may be expressed as linear combinations of vectors W1 through WK. But what do we have here? So we have that the first vector W1 was in U, and U was invariant subspace under the action of T. So from here we conclude that W2, which is T of W1, is also in U. But then if we apply T to W2, the result will be again in U. So what we get is that all these vectors W1, W2 up to WK belong to U. But the vectors U1 through UK may be expressed as linear combinations of W vectors, and so they belong to the span of W vectors. And all W vectors are in the subspace U. So this tells us that the vectors U1 through UK are in fact in the invariant subspace U. And that's exactly what we had to prove, because we knew by construction of our vectors that UJs belong to V lambda j. And now we prove that uj actually belongs to the invariant subspace U. So from here, we conclude that uj belongs to the intersection of V lambda j with U, which is our subspace U lambda j. And this proves the first property here, that every vector can be decomposed as a sum of vectors from U lambda j's. For the second part, so to prove the uniqueness of such a decomposition, we note that V decomposes in the direct sum of V lambda 1 plus V lambda k, and this tells us that even this decomposition is unique. So we have a unique decomposition with components in bigger spaces V lambda j. Thus, the decomposition with components even in smaller subspaces, U lambda j's, must be unique as well. And this completes the proof of this theorem. We can use the theorem we just proved to establish the following result. Theorem. Let T and S be two commuting diagonalizable operators on a finite dimensional vector space V. Then they are diagonalizable simultaneously, which means that there exists a basis B of the vector space V, which consists of joint eigenvectors for T and S. So which means that each eigenvector from this basis is simultaneously an eigenvector for T and an eigenvector for S. Let us give a proof. Denote by V lambda I eigenspaces for T, and by U mu j eigenspaces for S. We know that operator S is diagonalizable. So this means that our vector space V may be decomposed in a direct sum of eigenspaces for S. So V is equal to direct sum U mu 1 plus U mu k. And we saw that each S eigenspace is an invariant subspace for T. So this tells us that each subspace U mu j is invariant under T. So this is something that we proved earlier. Now T is a diagonalizable operator, and we have an invariant subspace. So we apply our previous theorem that described invariant subspaces for diagonalizable operators. And we get that this eigenspace U mu j may be decomposed in the direct sum of U mu j intersection with V lambda 1 plus ... intersection of U mu j with V lambda m. And now, combining this with the decomposition of V into a direct sum of U mu J subspaces, we get that we have the following grand decomposition. So V is the direct sum over I and J, intersections of V lambda I with U mu J. These intersections consist precisely of joint eigenvectors with eigenvalue lambda I for operator T and eigenvalue mu J for operator S. And finally, so choosing a basis in each space V lambda I intersected with U mu J, we get a basis B of the space V consisting of joint eigenvectors of T and S. Since V decomposes in the direct sum of these subspaces, we know that by joining these bases together, we obtain a basis of the whole space, and this basis will have the required property that it will consist of joint eigenvectors. So this means that these operators T and S will be simultaneously diagonalizable in the same basis. In terms of matrices, this means the following, that if A is the matrix of T and B is the matrix of S, then the commuting property means that A times B is equal to B times A, and we know that both A and B are diagonalizable. The claim that they are diagonalizable in the same basis means that there exists a common invertible matrix C such that A is written as C times D1 C inverse, and B is C times D2 C inverse. D1 and D2 are two diagonal matrices, but what's important here is that this change of basis matrix C is the same in both factorizations.